A definition for friction. Objects rubbing against each other. There would be friction. What happens when you rub your hands together really, really fast? Yeah, and if you can do it really fast, they catch on fire. So, one of the examples it says in here is a match on a striker strip. What happens if you don't get enough friction? It don't light, yeah. So if you wet it, maybe that would reduce the friction. Yes. In an engine, do you want friction? You want to reduce it. How do they reduce friction in an engine? They lubricate it with oil. Yeah. So we kind of know maybe what this term kind of means. What does it mean definition-wise? As far as we're concerned, it's a resistance. Well, resistant. Here's the key word. Force. Is a resistant force to direction of travel. So yeah, it can mean a match. It can mean rubbing your hands together. But we're kind of more concerned about things that move, things that are interesting. See this? What am I doing right now? Really weird. How would that be possible if there weren't any friction? Would you?
Your feet would just slide.
If there's no friction between the bottom of my shoe, which is rubber, nice kind of compound we use when we don't want lots of friction, and this floor, what would happen when I try to go that way? What does Cole do to push away on his ice skates? Does he put them straight like this and go like this? No, he turns them sideways so he can actually get some kind of grip there, right? But you know what happens? You've all done that in skates. And the first time maybe you get on them, you try doing this. Not all the friction between ice and the steel, which is weird because they're both solid. And you think usually two solids rubbing together, there's quite a bit of friction. But how skates actually work is because there's so much pressure, it actually melts that ice, and you actually got some lubricating film there. You got a tiny film of water that the skate glides on, and by the time you've skated away, it's already frozen over. If you ever thought about it. Anyway, there's friction. We like friction in a lot of places. On a bicycle, where do you want friction? Tires in the road. Okay, give me another example where you want friction on a bike. Brake pads in the wheel. Good. Otherwise, how are you going to stop? Do you oil your brake pads on your car? Not if you, unless you don't like them. Where else? Your bum in the seat. Yeah. You don't want to lube that up, do you? No. How do you steer? Your hands in the handlebars. Tons of places you want friction. Where don't you want friction on a bike? Pedals in your feet? The gear stuff? Yeah, you want to lubricate the chain so that there's as little friction as possible. When we did our balloon cars, you want as little friction as possible. Then it'll go farther, right? Okay, so that's friction. It's a resistant force to the direction of travel. So if that's my balloon car, and the force of the balloon, which is pushing the air left, causes it to go right, friction is in the opposite direction. Okay? It always opposes the motion. Okay? Does that make sense? Always in the opposite direction of the travel. This I'll talk about in a sec. This is actually called something. It's called a free body diagram. So why do we need friction? Read that. So Galileo, being a smart guy that he was, he came up with this theory that if there was no friction, well, look at our definition. If there's nothing, if there's nothing to oppose the motion, then what's going to stop its motion? In other words, this tape, if I hit it and there's no friction, when does it stop? It doesn't. And that's one of Newton's 3 laws too, we'll see in a sec. Okay? It'll keep going forever and ever and ever and ever, just like it would in space. Okay? So he's the first guy to theorize this, and it seems really weird, but it is a law of physics. Okay, there's 2 types of friction. Static friction and sliding friction or kinetic friction. This is the one that's in your formula. This is the one we're concerned about. You guys ever like moved when your parents help move stuff? You notice like if you're trying to move the fridge, it's really, really hard to budge at first, but once you get it moving, it's a lot easier. You ever notice that? Or with big items? Okay, like this table here. Excuse me, Liz. It's really hard to break it, but once you do, it's a lot easier. It takes a lot less force to keep it moving. Can I do that again? Okay, that's static friction versus kinetic friction. Static is always going to be larger than kinetic or sliding friction, okay? Just one little thing to kind of stick in your head. But when we're using the formula, we're assuming there is no static friction. If it's not already moving, we use kinetic, okay? So after you got this down, you can kind of forget about the word and just call it friction. Okay. Little demo. Now we're going to draw. I got a hole punch. So, what are the forces acting on this hole punch right now sitting on the table? Gravity. Okay. Now, we haven't done it yet, but one of Newton's laws says if there is an unbalanced force, it's going to accelerate. Is this thing accelerating? So there must be a force balancing that force of gravity down. We have a name for it. It is called normal force. So here's my stapler, okay? Just draw it as a box on a table. There's a force down, force of gravity, and we can calculate that because we know the formula, right? What's the formula? Yeah, mg. We're assuming this is on Earth. G is 9.8. What's the other word for little g again? Gravitational field strength. Yeah, here at the surface of Earth it's 9.8. M, well, I could find the mass of this hole punch in kilograms and we could find out F of G. But what we want to know is, not we want to know, but this new thing we call the normal force. Okay? It's not moving, it's just sitting there on the table. So the forces have to be balanced. Up and down. Now, what if I put a sideways force on? I'm going to push this thing, or maybe Colton could push it. Push it a little bit left. We're going to call that an applied force. Now, which way does the force of friction go? Okay, Colton here is pushing this thing, but we want to write the arrow. I don't want to write the arrow like that. I want to put it like this. If he's pushing on that, remember that's a definition of a force, a push or a pull. That's the applied force, or just FA. What opposes that? Force of friction. It must, because I know this thing stops after he pushes on it. Okay, so how much applied force does he have to put on this thing? What do you think are the factors that determine how hard this thing will be to push? Factors, not units. Air pressure. Like, he's pushing this thing. It's actually kind of sticky, isn't it? Like, it's surprising how much you actually got to push on it to make it move. Okay? So, what are the factors that determine how easy it is to push? Friction, which is determined by, well, friction itself has to do with the materials. That's it. We got a word for it. It's called the coefficient of friction. Okay, there's a little table with a bunch of numbers there. So that doesn't change. But what else is going to affect this thing? Someone said gravity? Okay, so it would be harder on Jupiter for sure. Try pushing it now. Come on. Come on. So what's affecting that? How hard it is to push? When I put my weight on this thing, these are the same two surfaces. The coefficient doesn't change. The friction between these doesn't change. But this definitely does, doesn't it? Okay? The amount of weight on it. That's the two factors that affect how hard it is to push. So when I'm talking about the force of friction, there it is. The force of friction is mu. That's a Greek letter, like pi, only it's not pi, it's mu, times the normal force. Okay? This mu is called the coefficient of kinetic friction, or just the coefficient of friction, because we won't be using static in this formula, like I said. All right? What is the normal force, though, if this thing's sitting on the table? It's not moving up or down. There's no unbalanced force. So it's equal to the force of gravity. Okay? So the normal force is the force of gravity. Okay? These two factors. The more I push on there with Fg, the greater the normal force, therefore the greater the force of friction. Also, it depends on the materials. Have a look at this little table. Wood on wood, they got a coefficient of 0.25. Steel on steel, twice as much. You see mathematically, the larger that mu is, the larger this number, the larger the force of friction. Okay? So what happens if I take, let's say that thing was steel on steel, it was 0.5, and then I want to move that a little easier. Calvin comes up there, squirts a little oil under it. Now it's gone down by a factor of, right, 4-fold. It's going to be a lot easier to push. The force of friction, if that's a 0.1 versus a 0.5, is going to be quite a bit less, right? This is one here I don't really agree with. Rubber on asphalt, you want a pretty high friction here, don't you? That's why we make tires out of rubber. Shoes usually are some kind of rubber compound. I'm thinking that's a typo. It's got to be higher than that. It's about 0.8, I think. If it's wet, if you guys are driving, you know you brake on a wet road, it doesn't stop as quickly, right? Because there's lubricant on that dry asphalt. Okay, rubber on ice, steel on ice, this is skating. If you got a nice clean ice and nice fresh skates, you know you can push maybe 5 times and you can coast quite a long way, right? Not very much coefficient of friction. Yeah, I know that's kind of odd though, but you won't get much traction, would you? How do you carve something rubber into the ice and make a sharp turn? Yeah, you might have a point. I don't know. This is just the table I get. Okay? But puck's out of rubber. It wouldn't be good if it was steel, would it? Probably not. Okay, so let's do some problems. the coefficient of friction between a wood box and a concrete floor is 0.3. Coefficient is mu. That's what it's telling you. With what force must you push to slide the box across the floor at steady speed if the force of gravity on the box is 450 newtons? Okay, every question you should be doing one of these. And on the next quiz I give you, if you don't, you're going to lose marks. Force of gravity on the box. That's down. That's 450 newtons. Okay? Now, is this thing moving down? No. So there must be some force opposing the force of gravity. What do we call that? Thanks, Jeff. Normal force. Yeah, we'll talk about that when we get to Newton's third law. Okay, the box is pushing on the table, so the table's pushing on the box and all that kind of stuff. Okay. This is also 450 newtons. These are balanced forces. Now I'm going to try to come and unbalance this. I'm going to push it. Okay? With what force must you push this? Now this is important. Very, very critical. At a steady speed. This thing has a force of friction on it right now. If the force that I, or Colton, pushes on it is not bigger than the force of friction, it's not going to move. The only way this thing's going to start moving is I have to exceed the force of friction. Then it starts to move. So this wording here, steady speed or constant speed, this means something. This means that the applied force at least has to equal the force of friction. If it's bigger than it, this thing will start accelerating. But it's not accelerating, it's saying steady speed. So these must be equal. Okay? So having said that, let's read this. If the box is moving at a constant speed, the forces acting on it are balanced. What's another word for balanced? Equal. Okay? This means the force top push, the force needed to push the box is equal, okay, I don't know, is equal and opposite to the force of friction. That's what I wrote right here. Okay? Important key concept. Got to know that. And in Physics 12, when we're actually going to accelerate these things, if you don't know that, then you're going to be lost. So what opposes the force applied? The force of friction. Okay? So here's my formula. Force of friction is mu times Fn. But I do know Fn is Fg, and I do know the force of friction is Fa. Okay? Mu is 0.3, Fn is Fg, that's 450 newtons, and 0.3 times 450 is 135. But because the force of friction is equal to the applied force, then that's the applied force you must push to get this thing to move. Anything less than 135 newtons, it's not going to move, because that's the force of friction. Okay? Does it make sense? You have to exceed the force of friction, otherwise it ain't going to move. Okay? I'll give you two more, and then you get some on your own. What is the force of friction on a wagon's wheels if it takes 30 newtons to move it at a constant speed? So this is an art. Okay, there's my wagon. Just make a box. What are the forces on this? Draw a free body diagram. I know it's got weight down. I know that's balanced with the normal force. It's telling me it takes 30 newtons to move it. That's the applied force. But do we see anywhere in here the wording that says constant speed? Yes. That means what? Okay, key concept. FA is FF. That's the only way you can really solve these problems. Okay, if you don't have that knowledge, you can't do it. Doesn't make any sense. Okay, so the force of friction is the applied force. And I know my formula is this. This is actually a trick question, isn't it? It's not asking me for the coefficient. It's just saying it takes 30 newtons to move it. What's the force of friction? 30 newtons is 30 newtons, okay? That is the force of friction because it's moving at constant speed. I almost tried to do more with this question than what they want. 10 kilograms of candy sitting on a floor. There it is. Free body diagram. Do you know the force of gravity of a 10 kilogram box of candy? Do we have a formula for Fg? mg. What's the mass? 10. What is g? 9.8. Okay, this box of candy weighs 98 newtons. What else do I know? Is this thing moving up or down? So there's something balancing that. It's called the normal force. And how much is the normal force? It's 98 newtons. Read the rest of the question. The coefficient is 0.3. What force is needed to move the box? Right now it's stationary. To move it, what do I have to do? I have to overcome the force of friction. So theoretically, I must just exceed it. But for simplicity's sake, let's say I'm just going to equal it. Okay? That's the concept. What's needed to move the box? If I push it with the same force of friction, it's going to move. Here's my formula. But I know Fn equals Fg because it's not moving up or down. And the force of friction is equal to the applied force. So I can say this. So what's the force needed? It's a product of mu and Fg. 0.3 times 98. Which is what? 29.4. Does that look right? Yeah, it does. A third 98. And what unit is Fa? Force is in newtons. Okay? I forgot to put this on there. So I have a sheet for you also called free body diagrams. We've seen the examples when something's sitting on a table. What about something not sitting on a table? Okay, it's a flying fish. Yes, that's right. No, it's an airplane. Makes actually a difference in this question. When I say free body diagram, better? Oh God, whatever, it's not art. What are all the forces on this plane? What's the easy one? Gravity. Is this plane resting on a table? So we don't call it the normal force, but hopefully this thing's not falling. It's flying horizontally. There's got to be something. What do we call that when it's a plane? Awesome. Lift. That's what the wings do, and this is aerodynamics, but when you change the shape of the wing, because the air to get around here must go faster than the air on the bottom, it actually creates lift. Because fast air creates a vacuum. That's how it works. But anyway, this isn't aerodynamics. Okay? What about motion sideways? That's motion up or down. That's got it covered. What's causing this plane to go? You can call it applied force, or if there's an engine involved, a lot of times they call it thrust, right? But FA, that's just fine. Okay, so that's what's causing it to go that way. Does he just fire his engines and turn it off and this thing keeps going? Or is there some force opposing it? Drag, air resistance, both are fine, okay? Those are both forms of friction though, right? So let's just call it friction. Air resistance is a form of friction. You like to have a parachute when you fall. It creates friction, slows you down. If there was no air particles to hit, it wouldn't help, would it? Okay, so just because something's not on a table doesn't mean you have a bunch of forces there. Okay? Okay. So, numbers, you do these. And, whoop, that's page 88. Just a sec, let me write this down. Page 92, 1 to 6. And I will hand you a free body diagram worksheet. I'll go over tomorrow, okay?